Hello again, and welcome to day 2. We're going to continue with the idea of continuity, and so let's again just talk about the definition. We've talked about it day 1, but let's talk about it day 2. The definition is that a function is said to be continuous at x equals c, provided that the following conditions are satisfied. We have 1, limit as x approaches c of f of x has to equal a. 2, so the limit exists. 2, a function has to be defined, so f of c has to equal b. And 3, we know that the limit exists, and then the function is defined, we have to fill in the holes. So we know that b has to equal a, or a has to equal b. Either way you want to write that does not matter to me. I have a bunch of theorems here that you guys can read on your own, but we've talked about this. A rational function is continuous everywhere the denominator is not 0. Polynomials are continuous no matter whether we add polynomials, no matter whether we subtract, multiply, or divide. Granted that g is not 0, there everything is continuous. And so we now need to prove that something is continuous based on these 3 stipulations. The first example, we're starting off extremely simple to make it easier for you guys. So yes, I know the first example may seem a little, I don't know, whatever we want to call it, simple. I'm doing it just to show how we do it. Given f of x equals 5x cubed, prove f of x is continuous at x equals -2. Notice, this is a polynomial. You could state that due to the theorem, it's continuous. I'm trying to show you guys how we're going to actually do it. So 1, we have to prove that the limit as x approaches -2 of f of x equals 5 times -2 cubed, which equals -8, -40. That's the limit. Why can we do that? It's a polynomial, you plug in. That's always what we want to do first with the limits, just plug in. So we get the limit to be -40. That's step 1, or condition 1 that's satisfied. Condition 2 says, what is f of -2? Well, we know f of -2 is 5 times -2 cubed. Well, we know that's -40. And so we satisfied condition 3. Condition 2 states that the function has to be defined. The limit exists, the function is defined. Condition 3 now states that the limit, as x approaches -2 of f of x, has to equal f of -2. And we know that's true since -40 equals -40. Limit, functions defined, they better be equal. That's how we're going to look at these functions that may not be so similar. Now here's one of the things that we have to realize. If you are going to try to prove that it is continuous or not continuous, you only have to dissatisfy one of those 3 examples. If you prove the limit doesn't exist or prove it's undefined, you're done. You don't need to go any further. So here, prove that it's not continuous. Well, I see a denominator. What I'm going to do is show that f of 3, equals 27 minus 27 over 3 minus 3. Well, that would have worked nicely if it wasn't indeterminate form. But if it's in indeterminate form, when we're solving, we know that since the denominator equals 0, and we're not looking for a limit, we know that since this is undefined, and so it is not continuous. At x equals 3, because f of 3 is undefined. You're done. That's it. So, you proved it wasn't continuous. Now, is this function, moving on. Is this function continuous? Well, we have a piecewise. Notice that this is from the left, this is from the right. Two ways you can do this. You could graph it. That's fine to graph it. It takes a little more time to graph it. So we're going to just go right to limits. The limit as x approaches 4 from the left of f of x equals this portion of it. And so we are going to plug in 4 squared to give you 16. We're going to also look at the limit as x approaches 4 from the right. This is from the right of f of x. That's going to give you 20 minus 4, which equals 16. Also notice that we know that f of 4 equals the limit as x approaches 4 from the right, because it's equal to here. So we can say that the limit as x approaches 4 of f of x equals 16, which also equals f of 4, and so therefore f of x is continuous. So say condition 1 satisfied, condition 2 satisfied, condition 3 satisfied, because they're both equal to 16. Also notice that since x is less than 4 is a polynomial, and x is greater than or equal to 4 is a polynomial, that everywhere else is continuous. So if we want to get really specific, we could state, since x squared is a polynomial, all values less than 4, f of x is continuous. Since 20 minus x is a polynomial, all values greater than 4 is continuous. And so we just proved that at 4 is continuous, and therefore f of x is continuous. That's if we wanted to be really specific, that you said for all real numbers it's continuous. Moving on, again, left, right, less than, greater than. So limit as x approaches 1 from the left of f of x equals 1 squared, which is 1. Limit as x approaches 1 from the right of f of x equals 1 minus 1. Oops, sorry, 1 minus 2. Let's try there to get negative 1. F of x is not continuous because the limit as x approaches 1 of f of x does not exist. And you're done. So you either have to prove the 3 conditions or prove one that is not true, as we did here. It's undefined. Here the limit does not exist. So that's proving it's continuous. The last part that we're going to look at here is find the values for k that make it continuous. Now, again, this is a polynomial that's not defined at x equals 2 because of the denominator being x minus 2. This is where the function is defined. K is where f of 2 is defined. So what we need to do is find the limit. The limit as x approaches 2 equals f of x, equals the limit as x approaches 2 of x minus 2, or of x minus 3, because the x minus 2's cancel out. And so we're left with that, which equals negative 1. So we know the limit as x approaches 2 of f of x equals negative 1. We know that f of 2 equals k. I messed up, guys. I did not move it up. There you go. Just trying to be good about it. We proved that the limit, we know where it's defined. What do these two have to be? K has to equal negative 1. And so what is k? K is negative 1. The last bit here, same idea. Now this one's a little more in-depth. I'm going to start you off. I want you guys to finish it. We know the limit as x approaches 0 from the left of f of x equals notice that we're plugging in 0. 2 times 0 plus 12k squared, which implies that the limit as x approaches 0 from the left is 12k squared. Okay. Limit as x approaches 0 from the right of f of x equals 5 sine kx over x. I probably should have a limit here. Well, guys, we're getting back into it, and I know we didn't leave a lot of room. How do you do this? I will start you out. 5. Pull the 5 out. Limit as x approaches 0 from the right of sine kx over x. Please finish this. What was the rule that we learned? Okay. Figure out what we need to multiply that by. Set the two limits equal and figure out k. Good luck, and I will see you in class.